We're talking about exchange economies and general equilibrium in exchange economies. An exchange economy is one where there's no production and each consumer is endowed with a vector of endowments, which is how much of each good does she start with in the beginning, by no choice of her own, just by virtue of having been born a farmer or something. And then we're thinking about an equilibrium is a price vector and a set of allocations such that the allocations are feasible. The final consumption of each good summed across all the consumers does not outsize the initial amount of the good present in the economy, which is the sum of the allocations, the endowments across consumers, and also the the endowments, the allocations are the while raising demand of the consumers given their income, where income is defined as the value of their endowment under the price vector P. So there's two both critically important criteria for something to be in equilibrium. One, it has to be feasible. That's really technical, technical in the sense that it's a physical limitation, right? It's a technology, it's a limitation on technology. But second, and more conceptually, is that the demands are optimal, right? The allocation cannot be made better, right? Given the prices that I face as a consumer, if I sell everything and then I demand back the optimal thing, so I trade what I have for what I would want maximally under that price vector, that is in fact what I get, right? So there's no way for me to do better by selling my goods and buying different goods in the market. So we're going to actually make a further simplification. We're going to assume that there's two goods and two consumers. So there's two goods and two consumers, and that's it. And this allows us to have a graphical interpretation of exchange economies. Of course, it limits severely what we can talk about, right? There are many very interesting cases where there's many consumers, many goods, potentially maybe infinite many goods, infinite number of consumers, where all sorts of things matter. But right now, what we're thinking about is just two goods, two consumers, and it's going to allow for a very parsimonious graphical interpretation. So what does that look like? Let's talk about consumer. So there's two consumers. So there's I equals 1 and I equals, well, we'll call them I and J. There's consumer I and consumer J. And there's good 1 and good 2. So this is our consumers, and this is our goods. Now, we can represent, as we've always done, the consumers in difference curves and budget sets in a two-dimensional plane. So let's take consumer 1. So this is consumer I. And consumer I has a preference over the two goods. So this is good 1, so x1, and this is good 2, x2. And here is the point 0, 0, right? So this is if she has 0 amount of both goods, right? Now, consumer I, we had some endowments. We had endowment of consumer I in good 1, and we had consumer I in good 2, and then we had consumer J in good 1 and consumer J in good 2, right? So those are our endowments, and that means the total endowment is equal to, I'm going to call this omega 1 is equal to omega I 1 plus omega I2, J1, and omega 2 is equal to omega I2 plus omega J2. So these are our total, this is the total amount of the goods in the economy, right? It's the amount of good 1 that I had plus the amount of good I1 that J had, the amount of good 2 that I had plus the amount of good J2 that J had. That's the total amount of good I1 and good 2. So the maximum amounts that are available are something like here. We could put them at the ends. I'm going to actually erase, this is just good 1 and 2, but I don't want to put xi because that's what we're denoting the allocations with. So on the horizontal axis, for good 1, we have good 1, and the maximum amount would be the maximum amount would be omega 1. Right? Omega 1 is the total amount available for a good in the good 1 market. So the maximum amount of good 1 that's feasible is this point here, omega 1. And likewise, we can draw the maximum amount. This is really, it's just omega 2. All right, so this is the consumption space for consumer 1. Right, these are the feasible allocations, not from a budget perspective, but from a purely technologically feasible perspective. This is everything that could be chosen. This is how much of the two goods there are. Any point in this square, any point in this place, it corresponds to some allocation that consumer I gets, right? Consumer I gets some amount of good 1 and some amount of good 2, and it can't be further along either axis than these two limit points, right? And so she's going to have some indifference curves looking things in here. Now we could also look at consumer 2, right? Consumer J. Consumer J has pretty much the same thing going on. So try to make it a little straighter. Right, this is omega 1, and this is omega 2, and this is 0, 0. And she might also have some indifference curves. And they're potentially different looking indifference curves, right? She has a different utility function. But they have the same consumption space, right? The maximum amount that either one of them can consume is the same. It's the total endowment in the economy. And it doesn't depend on who their identity. I mean, what they can feasibly, there's a different notion of feasibility, which is their budget, right? What they're able to afford once they sell all their goods depends on the price vector, depends on their particular, each individual consumer's individual endowment. But the total amount in the economy, what is technologically or physically feasible, is the same for the two consumers, right? Now notice something, that if consumer 1 is sitting at the point 0, 0, at the origin of her axes, that means that consumer J has everything, because there's only two consumers. So if consumer 1 is consuming 0 of everything, then consumer J is consuming omega 1 of good 1 and omega 2 of good 2, which puts her at this point here, right? So this point here, which is the maximum amount, corresponds to the minimum amount for the other consumer, right? And same way, if consumer 1 is consuming half of omega 1 and all of omega 2, then that consumes of half of omega 2 and 0 of omega 1 for the other consumer. So we can do this neat trick where what we're going to do is we're going to take this axis here and we're going to rotate it 180 degrees, and then we're going to plop it on top of and I don't know what happened here to my axis down here, but we can redraw it in. And now we have a nice, what's called an Edgeworth box. And it's a little messy, so we'll clean it up in a second. But we have an Edgeworth box. An Edgeworth box is a two axes, but rotated 180 degrees on each other so that the points correspond, right? So let's think about what happens if we have some point here in the economy, right? What does this point represent? Well, if we drop it down to consumer 1's axes, this says that the consumption of consumer I in good market 1 is this level here. That's the consumption. This squiggly line is the consumption of consumer I in good market 1, and likewise this is x. The point there is xi2. That's the consumption of consumer I in good market 2. But we can do the same exercise going to the other axes, right? On this side, we have that, and remember, we're measuring from the origin. The origin is the opposite side, is the opposite corner of the box. So this is the consumption of consumer 2. So this is x2 1, and this is x2j. It's a j, right? So this is x1j and x2j. Now notice that we have that the allocations naturally sum up to the initial endowments, right? Because if we add together x1i, x1i, x1i plus x1, x1j, right? So that's here. We get the entire length of the box, and the entire length of the box we decided was omega 1, which was equal to, by definition, omega I1 plus omega J1, right? And the same thing for the vertical axes. The endowments represented the length of the vertical box, the vertical leg of the box, and the point, any position has some vertical combination. It just splits the box into two, right? And the upper half is the consumption for consumer J, and the lower half is the consumption in that particular market for consumer I. So we can see here that we have a very succinct representation of this economy where we have a box here, and this box, each point represents a possible allocation, and the box itself represents the initial endowment, right? And everything, so on the bottom, below the point is the consumption for consumer I, and everything above the point is the consumption for consumer J, being measured from the other extreme corner, right? The origin from looking in this perspective rather than in that perspective. So this is kind of messy because I've drawn a lot on top of it, but we can just generally plop these things down. Now, we could think about what does a price vector do in this economy, right? In this Edgeworth box economy, we can draw in price vectors. So let's put in let's go back and draw a clean box. So we have our box that looks like this, and this is our 0, 0 for good I. This is our 0, 0 for good J, and this is our x2, and this is our x1. Right? Or maybe I'll put in omega. I'll put omegas, not x's. This is our good market 2, and this is our good market 1. Good market 1. Now, what is a price vector? A price vector is a ratio. What matters is the ratio of the prices, and that's how much can I exchange good I for good J, or how much can I exchange good 1 for good 2, right? So if the price of good 1 is really high, then we have a steep slope, right? I mean, think about just a budget set for so a budget set for consumer 1, right? Might look something like this. And this is, given the prices, this is the rate of exchange for, so I give up, right? This is P2 over P1. But notice that if we flip the whole thing, we can look at the same thing here. The slope is also P1, P2, right? So the slope represents both the rate of exchange from this perspective, looking at consumer I, and also this perspective, looking at consumer J. So the slope here determines a budget set, where this is the affordable region for consumer I, and this is the affordable region for consumer J, right? So, and I mean, it's supposed to be a sharp, it's not supposed to be this gradient. I mean, I'm just not precise enough with my tools. But so this is the budget set, right? In some sense, this is the budget set of consumer J, and this is the budget set for consumer I. And this makes sense, right? You can always afford nothing here, or consumer J could always afford nothing up here. And the frontier, the rate at which you can exchange, is given by how can you exchange good I for good J, right? How much can how easily can I exchange good I for good J? And whatever consumer I can exchange good 1 for good 2. Sorry, the goods are 1 and 2. Whatever consumer I can exchange good 1 for good 2, consumer J can as well. And so they're looking at the slope from the opposite perspective of trading in the other direction, but for the same slopes, right? For the same ratios. And I say the other direction because a movement along here is a trade. J is getting more of good 2, right? They're moving up, and less of good 1, and they're moving this way. Whereas consumer I is getting less of good 2 and more of good 1, right? So a movement in one direction for J is the opposite movement for I, and that makes sense because they're actually trading with each other, right? Now they're trading via this intermediary price mechanism. They're selling to the market and buying back. But selling to the market and buying back when there's only 2 consumers is really just tantamount to trading X good 1 for good 2. I guess I do X and Y for the 2 goods, but I didn't. It doesn't matter. So this is the budget sets, right? Now, where is this budget line located, right? The wealthier the consumer, the wealthier the consumer, the larger the budget set will be, right? So if we fix the total amount in the economy, so omega 2 and omega 1 are fixed constant amounts, right? So we're just deciding how much of it initially went to consumer I and how much of it initially went to consumer J. If all of it went to consumer J, consumer I can't afford anything. Their budget set is just this point, and consumer J controls the whole square. If consumer I starts with everything, then the whole square goes to consumer I and nothing to consumer J, right? So the budget set is the whole square. And as we move the endowment from consumer I to consumer J, we're pushing this. I guess if we're moving the endowment from consumer J to consumer I, we're giving I more power over the square, and so we move up the budget set, right? The ratio of prices has remained the same, so the slope of that budget line stays the same, but because the endowment for consumer I is bigger, consumer I now has more affordable bundles. And consumer J, because we fixed the total amount in the economy, we've just moved it from J to I, J now has less affordable bundles. And so each line here corresponds to a different budget set, which is a different ratio of allocations between consumer I and consumer J. If we move, we change the prices. If we make I more expensive, we make good 1 or good 2 more expensive. That corresponds to a rotation of the budget set, right? The budget set will rotate, and the rate of exchange will change. That also changes what's affordable for the consumers. It also changes the income of the consumers because the consumers might have different amounts of the 2 goods to begin with. So if I have more good 1 than good 2, and you make good 1 more expensive in equilibrium, P1 goes up, I become wealthier, right? Because when I sell my goods to the market, I can receive more than I could before. And so this is the analysis of an Edgeworth box. Let's draw one more Edgeworth box, and let's talk about what an equilibrium looks like. So we start out with our 4-sided little box. And we know that so this is omega 1, and this is omega 2. And let's say that the price vector looks like this. Well, we know that for this price vector, we're just facing let's think about just consumer 1's problem. Consumer 1 has indifference curves that looks like this. And we know that their Walrasian demand is going to lie on the frontier of their budget set because we assume that utilities are, concave and continuous and strictly monotone. So we can apply Walras' law. We know that they'll spend their entire income. The income, of course, is endogenous now. The income depends on their endowment, but once they've sold it to the market, they have an income. They're acting like the standard consumer that we analyzed in September. And that consumer is going to spend her entire income. Therefore, whatever their Walrasian demand is going to be on this budget line. Now, consumer 2 has the same thing, has a set of indifference curves that look like this, right? And consumer 2 is going to have some optimal demand, and the optimal demand will lie also on that budget line. Both the optimal demand for consumer 1 and for consumer 2, given this nice, well-behaved preference model, is going to lie on the frontier of that budget. The frontier for one is the frontier for the other, right? Because what's affordable for one is whatever's not affordable for one is affordable for the other. Now notice that this is not an equilibrium. Why? Well, let's look at the amount demanded in good market 1. So in good market 1, that's on the horizontal axis, consumer 1 demands this much, right? This is X star of P, right? This is P. The ratio of the slope is P. P, and then I, which is P dot omega I. This is the income of consumer I. Their X star is that big chunk there. And we'll do the same exercise for the amount demanded for consumer 2, which is to here, right? Right. So the reason I'm doing this is where the demands fall, right? On the horizontal axis, and this is X star. I guess we need an I here. I'm doing the wrong color. J of P, P dot W J. Oh, that's bothering me, so I'm gonna make it an I. Now this is a perfectly well-defined while raising demand, but we're violating the feasibility constraint, right? Because X star I, which is this much, plus X star J, which is this much, clearly exceeds, is greater than the length of the thing, which was omega 1, right? And we can see that this length, maybe you can't see it in the color, this length, this piece of the rectangle, plus this piece of the rectangle, is bigger, right? It's bigger by precisely this much. There's an excess demand. And if we looked out in the other good market, we would see that there's actually an excess supply of good 2, right? There's less demand than there is supply in good market 2, and that's because the ratio of prices is wrong. This ratio of prices is not in equilibrium because consumers like good 1 more than the amount of good 1 that there is. The price of good 1 is too cheap. And likewise, the price of good 2 is too expensive because there's less demand than there is supply. So we can see that in this particular example, where this price vector does not constitute an equilibrium, and it doesn't constitute an equilibrium because the price of good 1 was too cheap, so there's an excess demand, and the price of good 2 is too expensive, there's an excess supply. What would an equilibrium look like? An equilibrium would look like a point where we have a budget line, and we have the while raising demand for both consumers at the same point. So where both consumers are jointly maximizing and demand the exact same point. Now their demands are not equal, right? Because the demand of good 1, the demand of consumer I is denoted on this axis, so it's here, and the demands of consumer 2 are on this axis, so it's J rather, is here and here. But the fact that it's the same point means that it sums up to some point that's feasible, right? So they demand the same point in this graph, but looking at from separate axes. And that would be an equilibrium. And we'll talk in the next video about the existence of equilibrium. We'll do a numerical example, and we'll talk about the existence of equilibrium.